Hello again and welcome. Today we're going to be looking at another CENTECH meter. This is item number 95670. This again came from Harbor Freight. We can see it accurately measures dwell angle, engine RPM, and it supports 3, 4, 5, 6, and 8 cylinder engines. And they claim the tachometer input is good for 10,000 RPMs. Let's just go ahead and open it up. Oh, comes with a nice little carrying case. Let's see, so it comes with a manual. Not real detailed. Looks like 15 pages. There's your temperature sensor. And one of the nice things with this, you can see they use the standard type input. So, you know, a lot of the meters that I use, they'll come with an adapter that you have to plug into the meter, and then you can plug your standard probes into it. And you can see it comes with the inductive clamp. Looks like this is the instruction manual for the inductive clamp. It's interesting, they sealed the meter itself, but not the plastic case. Let's just see if it'll... Oh, sure enough. You can see it powers up just fine. So recently I'd looked at another automotive meter. This is the EOSUN EM129. To give you some idea how the two meters compare, first of all, this CENTECH is sold by Harbor Freight. This meter costs about $30. Compare that with the EOSUN that costs about $110. I've seen it as cheap as about $90. The CENTECH is a 2000 count meter compared to a 4000 count. This is obviously manual ranging, and this is auto ranging. We can see it's marked Cat 2 600 volts, and we can see that's the same for this meter. It's also Cat 2 600 rated. Of course, this meter came with the inductive pickup. This one did not come with that accessory. Again, I don't know if that was a mistake on their part or not. So let's just do some basic checkouts with this meter and see if it works. So the first thing I noticed of this meter, it's similar to the EOSUN. When you go to plug these connectors in, they're actually quite tight inside of that sleeve. Again, that may provide some additional support. Let's start by looking at resistance. You can see the lowest range is 200 ohms, and it looks like that enables our continuity test. Yep. So I'm assuming if I zero this out, we're going to have to suffer through listening to this thing beep. You can see it's not very loud. Let's just compare how loud this is against my BM869S. So again, here's the CENTECH. And here's our Bryman. You can see this meter does not have a relative mode, so we can't zero out that error. This is with a 1 ohm resistor. That's what we'd expect, the 0.2 offset. This is with 50 ohms. Again, this is a 0.01% resistor. This is a 100 ohm. And this is also 0.01%. This is with a 1k ohm resistor. This is with a 10k ohm. This is a 100k ohm. This is with a 1 mega ohm resistor. And this is with a 10 mega ohm. You can see it's quite accurate, but very slow to settle. So let's just try the diode check mode. So we have to place it in the 2k ohm setting. So this is a single diode. And here is 2 diodes, so it can't read that. For those of you who want to see LEDs lit with your meters, it can slightly light the white LED. Let's just look at the open circuit voltage using the Bryman. Looks like about 2.44 volts. Well, I don't really have a good way to check temperature on this, so you can see I just got a couple of alligator clips, And you can see I'm using my fluke needle probes. So I'll just insert these to the jacks, and let's go ahead and enable this so the box will put up roughly 500 degrees right now. You can see it's quite accurate. Let's just dial this up. So this actually should be about 1020 degrees right now. And let's dial it down, and you can see 22 degrees. Unfortunately, this meter cannot measure capacitance. You can see the meter has a setting here for HFE, or the gain of a transistor. It's got this little socket where you can plug different parts into it. This isn't something I'd really have a need for. There really aren't a whole lot of other features on this meter. Let's have a look at the DC voltages. So again, this box will put out roughly 5 volts in this setting. And you can see that's dead on. Let's try it with the 200 volt range. And this is with the 1000 volt range. So in this setting, it's a square wave with a 2.5 volt bias, so we should be reading 2.5 volts. That seems fine. And this is AC coupled, so it should read 0. That looks fine. This should be roughly 60 volts DC. And if we change this over to AC, this should be reading roughly 70 volts. And we can see it's reading quite high. So let's just try it in our 200 volt range. And again, I'm going to apply a 5 volt DC signal. Wow, that's kind of crazy. So it's in the AC range. I don't have any AC voltage. It's a DC voltage at 5 volts. And you can see it's reading 10 volts here. So here you can see it. It's 5.00 volts DC with no AC in the upper right. Again, this will be a 0 to 5 volt square wave that is AC coupled with a capacitor. And you can see the Bryman now is reading no DC, but 2.5 volts of AC. And we would expect the same thing here. With this meter, it's reading 2.3. So this should be 60 hertz. And in the upper right, we can see it on the Bryman, 2.5 volts. Of course, this is not able to read down this low. This is with 120 hertz, and that's the limit of my box. And we can see the meter is getting fairly close there. Let's just compare this with our EOSUN meter. So 120 hertz again, you can see it's 119.97 versus 0.11. So just not a lot of resolution with this meter. And so let's have a look at the tach function. So again, I've got it set for 30 hertz, so we'll multiply that by 60 and then times 2, and that should give us roughly 3600 RPM for a 4-stroke engine. And we can see I have our EOSUN here set for a 4-stroke, and again this is for a 4-cylinder engine. We can see on the EOSUN it's reading 3598, or basically 3600 RPM. So this is an 8-cylinder engine. I would expect that to be half of this. Even if we took the 3600 RPM, multiply that by 2, I'd expect this thing to be 7200 RPM. I don't see anything in the manual about using this meter to read RPM. We can see it has the dwell angle and the tach specifications, but you can see in the back here it only has measuring the dwell angle. No mention of the RPM. So I would expect this thing would actually be able to read this. I show it being able to read all the way up to 10,000 RPM. And again, this EOSUN can read 2 functions at one time. So you can see I've got all 4 wires connected. In the upper right, I'm displaying the RPM. And then in the bottom of the display, we're looking at the frequency. So again, I'm applying 10 hertz. And 10 hertz times 60 would be 600 multiplied by 2. Should give us 1200 RPM, which is exactly what this meter is displaying. And again, our CENTECH meter is showing 29. You know, as disappointed as I was with this EOSUN meter, you know, it cost like $100 and they didn't include the inductive pickup with it. And it had problems being susceptible to the ignition noise, but you know, at least it threw up the right numbers. So I'm not sure what's going on with this meter. Let's go ahead and take this thing apart and have a look at it. I love the batteries that come with some of these meters. This actually appears that it's laid out for a 40-pin dip package. But you can see right here, you can see all those pads are solid. It looks like all the rest of them have the holes. So I'm not sure what they're doing there. Here's our chip on board right there. EOSUN. Remember when I first started testing this other meter? I went to their website and I had done a little research on it, and I had mentioned that that's one of the names that this company had gone by, EOSUN. I suspect that this is actually made by the same manufacturer of the other meter. Let's go ahead and pop this board out of here. These are tight. I can't get them with that screwdriver. Yep, that don't fit. Time to pull out the big guns. Whew. Those are tight. Oh, even there. Yeah, this meter's never been apart. Wow. Look how long those are. Those weren't going anywhere. So you can see I've just placed it into diode mode. We'll just draw an arrow on this thing. Let's have a good look at the contacts. First of all, there appears to be no sign of any lubrication on them. You can also notice again they've placed the vias right in the center of the pads. You can see the switch design itself is probably one of the more complex ones that we've looked at. Again, there's no lubrication on the top side mezzanine board as well. You can see it looks like it has 4 different potentiometers for the alignment. So our thermocouple input here. The current input they're showing on the circuit board here was a 10 amp 250 volt. Of course, the meter itself doesn't use a 10 amp fuse. There's nothing there. It looks like they might have had placeholders right here for it, but they've opted not to install that feature, so it's basically directly connected. And then we have a small glass fuse here. Again, that's 250 milliamps. Again, that's kind of sad because when we look at this EOSUN meter here, this came with a HRC Holly branded fuse. Again, this was rated for 80 kiloamps. I can tell you one reason that this thing is so quiet. They just have this piezo floating off of this piece of foam here. You can see they run this trace right from our 10 amp input right to this one side of the shunt, and it also runs up to the one leg of the fuse over here, and then this would be the other leg of the fuse here. So I believe that they possibly cut this section of the pad if they were going to insert the fuse. Notice here we actually have a couple of trim pots, DW and RPM. I would have thought that that would have all been digital, that there would be no analog adjustment for that whatsoever. I kind of wonder now if they're going to a frequency to voltage converter and then reading this with an analog signal. It's hard to believe they would try to pull something like that off. So I spent a little bit of time looking up some of the ICs used on this board. This is a part made by ON Semiconductor. It's a 14538B, and this is a one-shot. There's also a TL062 op amp, a TL555, there's a HEF 4011, and then a TL082. So yeah, I'm not so sure if they're not trying to do a frequency to voltage conversion with this. Looking over the rest of the meter, we can see here again is our input jack, and you can follow the trace right along here. It goes up to this PTC. That is basically the only input protection this meter has. Then it goes on up to a few different traces that go into the rotary switch. So again, if this were hit with a transient across these two lines, of course these traces down here are going to see the full effect of that. I expect the other side of this PTC here, which runs up to the switch up in here, is probably used for the diode and resistance modes. But essentially I don't see any other protection on the meter at all. The only thing I don't like about this is you saw what I had to do to take this out of the case. It looks like basically these 4 screws can remain intact. Those are just used for this bezel. But essentially this knob is basically press fit onto this shaft. It's quite a tight fit. Well, if you had to replace the fuse, this is sitting in the meter in this orientation, so this all has to come out. And as tight as this is, I'm afraid essentially you're going to have to pry this out. Of course, you've got these 2 latches up here as well that you're going to have to work around. It just would be a nightmare just to even get the fuse changed on it. Yeah, so I'm not very impressed with just the mechanical design of it. You can see it's just using the cheap stamped type contacts. You want to be very careful not to touch these. And the same for the mating surfaces. Alright, so you can see I've put the CENTECH meter back together. I've left the cover off. But I've noticed something interesting, and that's that I believe the meter actually does work. I've been spending some time reading the manual, and the secondary sheet that it comes with. So we can see here note number 4. It says figure 1 is an illustration for an independent cycling ignition 4-cylinder ignition system. To perform measurements, set the rotary switch of the automotive meter to the 4-cylinder range position. If the instrument clamps to the V high voltage line coil wire, which is between the coil and the distributor, the reading on the automotive meter display is the actual value of the RPM engine. If the instrument clamps on any ignition line, 1, 2, 3, 4, spark plug wire, which is after the distributor, then the reading on the automotive meter's display is obtained by multiplying the spark plug wire reading by the number of cylinders to obtain the RPM value. So in this case, it's a 4-cylinder engine, so we have it on 4-cylinder. We multiply this by 4, and sure enough, we're going to get the 10,000 RPM that I'm currently putting out, which is the 83.333 Hertz. So it does appear that it works. So let's just try to adjust this pot here and see how much we can move this thing. So yeah, that's about the end of it. You can go a little lower and a little higher, but not enough to make up for it. It's interesting that it does appear to be an analog function though. You know, why they would do that instead of doing it in digital, I have no idea. Again, for my own engines, they'll actually output a tachometer signal, so you don't even necessarily need to apply the clamp meter to the spark plug wires like what they show here. So the way that this meter is actually decoding that information is pretty much a standard. I'm not sure how come they came up with this method of actually trying to decode it. Now that we know that the meter can decode the RPM, I think what I'll do is go ahead and put the back cover on, and then we'll continue our testing. So off to my left, you can see I have the high voltage power supply out. It's connected to both the Brahmin as well as the CENTECH meter. Currently you can see I have the CENTECH meter set for the 20 volt range. Let's go ahead and increase the voltage a little bit. Again, the CENTECH is a 2000 count meter. Right there at over range. This will be the 200 volt range. And you can see it over ranges at 200. This will be the 1000 volt range. And this is the limit of our power supply, so just shy of 1000 volts. Alright, so I've restrapped our power supply to put out a 60 Hertz waveform. You can see on the Brahmin it's 552 volts, and you can see it's at 60 Hertz. You can see our DC offset is basically 0. So on our CENTECH meter, you can see it's displaying 0 volts DC and 606 volts AC. Again, this is a averaging meter, so if you take the 540 volts RMS, multiply that by 1 over the square root of 8, that'll give you roughly 600 volts, which is what this meter is displaying. So let's go ahead and we'll give it some DC offset. You can see there's basically 120 volts, and it has a pretty dramatic effect on the AC voltage on the CENTECH meter. Again, you can see on the Bryman that reads a constant 540 volts. Would expect the same thing with the DC. There you can see it's decoding it correctly, 74 versus 75, so the two meters match. So if you were going to use this meter, you'd have to realize that you'd have to switch it to the DC, subtract this number off your AC number, and handle that averaging conversion. You know, personally, I would rather have a meter that just does all this for you, but I could see some people not caring about this kind of a feature. Alright, so I have our two meters put in series, and you can see I have them both set to their 10 amp scale. So I currently have them attached to my bench power supply. Let's just apply a little bit of current to them. And this is the upper limit of this particular power supply. And you can see there's a little bit of variation between the two meters. So here again you can see both meters are in series, but I'm using the milliamp range on both. And you can see I'm applying roughly 42 milliamps. Let's go ahead and increase this a little bit. And fairly close. Let's just try it in the 20 milliamp range. So you can see again fairly close. This is roughly 1 milliamp being applied. Of course, this CENTECH meter cannot read AC current, unlike the EM135, which obviously has that feature. And so you can see I have both meters attached to our engine simulator. Because the EM135 can display two parameters simultaneously, we'll be looking at both the RPM as well as the dwell. And unfortunately the CENTECH doesn't have that feature, so we'll have to manually switch. So what I've done is I'm using a isolated output off of our simulator to drive this, so I can switch between different modes. So we'll go ahead and start up the engine. So again, we're at 300 RPM, multiply that by 4, gives us roughly 1200 RPM, which is what our EM135 is showing. Then the engine's warming up, and the idle's coming down. And this is kind of a pain. You'd have to again multiply this 25 by 4, so it'll give you your 1000 RPMs. It's just not a very accurate way of reading the engine RPM. Let's just turn off the audio for a second, and we'll go to our engine model page, and let's give it a little bit of throttle. And here you can see we're on the rev limiter. What we'll do is go ahead and put the motorcycle into gear. Let's just put it into 6th and release our clutch. You can see we're a little over 10,400 RPM or so. Looks like our CENTECH meter is displaying roughly 2,600. Again, multiply this by 4 would be roughly 10.4 as well. Let's just go ahead and try the timing. So again, if we go to milliseconds And this is currently looking at the dwell time. So you can see on our software this is roughly 1.33 milliseconds, which is exactly what this meter is showing. Let's look at it in angle. So it's roughly 42 degrees. And let's look at it with the CENTECH meter. So it's showing 89 degrees, but again, this has to be changed. So what we have to do is go over to diagnostics, and we're going to change this over to the ignition timing. And now you can see it's reading 10.5 degrees. Now the reason that this is off by a factor of 4 again is that we have to actually multiply this by 4 to get the correct number. I don't know why they set this up like this. The math should be fairly simple. In my opinion, again, I'd rather have the meter that can do all these calculations for you. So let's see. So that 42 degrees is our dwell time down here. You can see it's 42.8 or so. So yeah, this meter seems correct, and so does our CENTECH. If we want to change the amount of fuel, I'll just go ahead and drop the throttle. You can see our dwell time is now reduced. It's about 24 degrees, so times 6 by 4 give you 24. So let's go ahead and change both meters to look at the time that the fuel injectors are active for. Again, this would be the injection time in camshaft degrees, so roughly 15.4 degrees. And again, that's exactly what our EM135 is showing. And the CENTECH again is showing 3.6 or 7 degrees. Again, multiply that by 4 and you get roughly that correct number. So it looks like the CENTECH meter at least does show the correct numbers if you want to manually calculate them. Let's go ahead and turn on our ignition. Again, this is a multi-spark ignition, so the RPM is not going to read correctly. I just want to see if the meter will reset. Hard to really tell. It doesn't appear that it's resetting. It definitely doesn't like the noise, but let me go ahead and turn the RPM up enough where we can actually get a reading. So I'll set this to 6,000 RPM divided by 60. It should be 100 Hertz roughly on the Bryman. And you can see it's pretty much steady at 100 Hertz. Again, this would be roughly 6,000 RPM. And I know we're well above where the MSD ignition is using any kind of a multi-spark. You can see I've switched over to the EM135. And you can see it's displaying roughly 12,000 RPM. Again, this is for a 4-stroke. Nice thing with this meter is we can handle the wasted spark situation by just setting it to a 2-cycle engine. And we'll get the correct RPM reading with this. Unfortunately with this meter I can't really do anything. If it had a 2-cylinder setting, we could set it to a twin and it would actually display the correct amount, but unfortunately it'll only go down to a 3-cylinder engine. Again, you can see the RPM is low enough now where the ignition is multi-sparking. And again, both meters are not able to read this. You can see we are at roughly almost 1,000 RPM right now. Alright, so the last time I ran that ignition tester, you notice I'd had the nitrogen tank out. Unfortunately, I've depleted those tanks and I haven't recharged them yet, so I won't be able to run a test with that using this meter. So what I'm going to do in this test is use our transient generator to supply a 220 volt rectified AC signal. So we can just go ahead and turn that on. You can see the meter again is reading 527 volts. Of course, that's not correct. Let's try this with the DC volt setting, and you can see it's 238 volts. So what I'm going to do now is rotate the knob through all the different settings, and let's just see if this causes the meter to fail in any way. Again, this transient generator will limit to about 40 milliamps where this thing will shut the output off. Alright, that's it. Let me go ahead and functional test the meter. You can see I have our ESD generator out. Again, this generates a 4,000 volt peak at 15 amps, and it does it in sub 1 nanosecond. Basically, it generates a static discharge. So what we'll be doing is applying 5 transients, both positive and negative, and then we'll go back and functional test it. Again, we'll just change the polarity. And we'll repeat our test. Alright, that's it. Let me go ahead and functional test the meter. The meter survived the ESD testing just fine. What I'd like to do is actually transient test this meter. Unfortunately, these cheap automotive meters that I'm looking at are basically only Cat 2 600 volt rated. Typically when I run the meters on this generator, they're all Cat 3 600 volt and up. And again, this meter I'm sure would fail on this generator at a fairly low voltage anyway. Again, you saw that there was very little input protection on it. So I think what I'm going to do is just set this thing for a fairly low voltage. We'll just try a couple of kV with it. Again, this will be a 100 microsecond full width half height with a 2 ohm source impedance. Of course, when they're testing Cat 2, they're not using a 2 ohm source impedance. Again, this generator is a fairly low energy source. It's about 20 joules tops. It does not follow the IEC standards as far as the current profile, and it's about double the full width half height for the voltage waveform. So what we'll do is start with the frequency, and then we'll work our way over to the 8-cylinder selection for the dwell. Then we'll change the polarity and work our way back. So again, this will be 5 transients. And we'll go ahead and invert the polarity. Put a little clock out here to give you an idea how long this test is actually taking to run. Oh. You can see it just broke down. Oh. Yep. We just damaged the meter. So much for showing you how long it takes. Oh. Yep. It's totally hung. You know, it's 2,000 volts again. Peak. With a 100 microsecond full width half height and a 2 ohm source impedance. Again, not a very big transient at all. Again, if you've been watching my videos, you've seen many meters run above 10,000 volts. The Fluke 101, for example, I've had all the way up to 13,000 volts with a 100 microsecond full width half height. We actually had a member who had a combo generator for IEC that repeated those tests at, I think, 12,000 volts, and the meter survived just fine. So even some of the lower cost meters survived these tests quite well. I think what I'm going to do next is we'll take this thing apart and have a look at it. Well, I've been looking over the meter and I don't really see where it's breaking down at. It could just be one of the switch contacts. Again, that's a problem with some of these meters. They have a very high density switch. Of course, then things can break down quite easily. So I think what I'll do is just put this thing back together real quick. Then we'll apply the same transient and let's just see if we can detect where it's breaking down at. Alright, so you can see I have the polarity set the same way. I've just reset the generator for the same 2000 volt peak, and we're back in the 8-cylinder mode. So let's just try it here. Oh yeah, right here. Look right here. See? It's right at this contact. Alright, so you can see I have our transient generator attached. Again, because the switch is in this orientation here, so basically it's running across these set of contacts, I don't think that it really has anything to do with the mode that I was in. I could be wrong. What I'm going to do is just apply a 1000 volt strike across the two contacts here, and let's just see if this area breaks down. Okay, so that seems fine. Let's just go ahead and we'll increase this to the 2000 volt peak that I was running previously. Oh yeah, you can see right here. Looks like it's right between these two pads. Just not enough clearance right there. You may remember that I didn't run this across this transient generator as well, and that's because I basically have ran so many meters now, you can pretty much tell which ones are going to survive and which ones won't. I could believe that this one would not survive this same transient. So I had modified the front end of this thing. Actually, I've made other modifications to this meter as well. It looked like there was a design problem with it that I'd corrected. It used to be very susceptible to the emissions coming off of the ignition tester, and it would just continually reset. So I made a change to the design to correct for that, and it's actually quite stable now. Normally at this point, what I would do is hook this thing up with our half-cycle line simulator, and we'd get the high-speed camera out and we would just basically flash over these contacts and see what kind of damage the meter would have. I think what I'd like to do this time with this meter is pick a couple of contacts and run that life cycle test on it. You know, these contacts are still in very good condition. Again, this meter has very little wear on it right at this point. I think what we could do is just grab one of these pads, like up in this area here possibly. Alright, so I'm using one of the contacts that I pointed out. I think that's going to be a pretty good setup. You can see it just tacked our wires in here, and I'm looking at how this thing can go through the case. Of course, this one doesn't have any kind of an access hole. It looks like the seam around this meter is quite sloppy. You can see this is, I'm not really applying any pressure on this at all. And these just fit right together. So I think that's what we're going to do is just snug these down a little bit, and we'll just run it just like this and put the rubber boot back on it. Let's just see what we get for contact resistance. So it looks like about 0.36 ohms or so. Let's try it over here. Yeah, well over 100K. Of course, my fingers are touching the probes. A couple of meg. That's going to be just fine. So we'll go ahead and set this test up. Alright, so our meter has, it looks like, about 1,200 cycles on it so far. You can hear it's already starting to squeal a little bit. Let me just move the camera a little closer. Looks like we have about 5,000 cycles now on the meter. This is at roughly 7,000 cycles now. Alright, so the meter now has about 20,000 cycles on it. Currently we have just over 30,000 cycles on the meter. We're in the final stages of the testing. It looks like the meter now has about 43,000 cycles on it. So the meter finished up cycling last night. Unfortunately, I wasn't around when it finished up. Ooh. You can hear it's got a bit of a squeak to it. A little bit of debris that you're seeing around here is just the rubber wearing off. If you look right along this edge, you can see it's definitely wearing. Backside though looks pretty clean. Looks like the detents and the ball and spring assembly are all in real good shape just by the feel of it. Let's go ahead and pop this C-clamp off of here. And see, there's a little bit of dust around that, but again, nothing major. Well, you can see it's just got a little bit of rubbing that's gone on the edge. You can see we're starting to wear a little groove in there, but again, this is after 50,000 cycles. You're expecting there to be somewhere. Notice that they have different detents here. You can see they could move the balls to the inside groove. I wonder if they didn't use this case design for two different types of meters. You can see they definitely have some areas here for some dead stops as well. See what the second half looks like. Oh, see a little bit of dust down in here. There's definitely some grooves in a few of the pads. You can see it in the solder mask in this area here, but you know, really all in all, these look pretty good. See this up area right here, it's definitely got some deeper grooves. You can see like right here there's a bit of a groove, If I get the angle just right, you should be able to see it with the camera. Like right along the edge of this pad here. It's a pretty deep one right along there. Again, having these vias inside of the pads like this, you can see the damage that's causing. This is looking at the secondary switch. This is the one located on the mezzanine board. So it looks like we have cut through the plating on some of these. That's definitely signs of copper there. You can see how that's really chewing up this pad. And I'm not sure why they would put the vias in here like this. I mean, you can see there's quite a bit of wear, but I don't see a lot of metal fragments that I've seen on some of them that we've looked at so far. It's interesting, on some of these pads they actually put the vias off to the side, like this one here. You can see how the wiper contact would never actually drop inside of the via. Just down a couple more, and here we have one again. It's right in the center of the pad. So they're not very consistent with it. Here again you can see how it's eroding the pad, and we can see copper being exposed. Let's go ahead and load up the data we've collected so far. So this is looking at the raw data. I've added another feature here where we can look at this as the average. So essentially this is looking at a walking average of the last 50 cycles sampled. And the reason I'm showing this is that, for example, if you ended up with just a glitch, the meter still may not be all that bad. Everything I plot is the standard deviation. Again, this is for the last 50 samples. This is basically accumulating every single resistance measurement that I've taken for the 50,000 cycles. So you can see the green trace, for example, this is our CENTECH meter, and you can see how this just skyrockets all the way up to 7 mega ohms, and then it flattens out. This is where I've stopped the test at about 17,000 cycles. Looks like the other meters are all sub 500K up to about 3,500 cycles. Let's just have a look at our log data. So again, the purple trace up here, this is our fluke meter. This red trace, this is our Agilent. The gold trace here, this is the CEN test. The next three meters are kind of a wash. We have our baseline meter. This is our CENTECH. And here's the meter that we just ran. Of course, nothing I've tested so far comes close to the performance that the fluke has. This is again looking at our three-dimensional data. This is for our CENTECH 830. And this is our baseline meter. This is the Agilent, the CEN test, our fluke meter, and this is our EOSUN CENTECH meter. It's interesting, they all start out pretty good, and then they start to go bad, and then you can see where they improve. The CENTECH doesn't show that again because we shut the meter off, but you'll notice that with our baseline meter. The Agilent, again it improved. This is our CEN test. Our fluke meter just flat out improved. Again, I believe that this is partially caused because the wiper contacts start to seat into the pads and we get a better joint. Again, I believe with most of these meters where they're using the switch to control the power to the meter, I gotta believe once you start looking at even above an ohm, you know, the switch is basically bad. You know, certainly at 10 ohms, let alone 100 ohms where we're at here. Again, if we just kind of zoom into this area, let's just take a look at the first 2,000 cycles. So again, this green is our CENTECH meter, and this blue trace is the CENTECH EOSUN meter that we just ran. Again, this red trace is our baseline, and this purple is our CEN test. The white is the Agilent, and again the yellow down here is our fluke. So again, if we add the meter that we just ran, you can see it basically starts out about 300 cycles or so, and it just takes off. You know, this meter doesn't even come close to the performance of those 3 meters. So the next thing I'd like to do is drop test the meter. This is the battery that was included with the meter. Somebody was concerned with the last drop test that I ran because I'd used the batteries that came with the meter. They thought these were quite a bit lighter than a standard name brand battery. So let's just see if that's true. So this is about 35.5 grams. Looks like about 45.7, 45.2, and 45.2. As you can see, I've reassembled our meter. We're going to be drop testing this using our heaviest battery, the Everready. And you can see it still powers up. It does show a low battery. Again, that's not what's wrong with the meter. We'll try a few different axes. See, it still turns on just fine. And besides the battery, nothing else is loose. Alright, let's have a look inside of it. See if we've caused any additional damage to the meter. Yeah, it looks like the fuse is still in place. Again, I dropped the meter right on the face. If anything was going to knock that loose, that would have been it. Even our little speaker stayed in. I think what I'd like to do is run this thing on our half-cycle line simulator next. But I think when we do this, because we know that this mezzanine board will arc over in this area here without the rotary switch even in play, what I'd like to do is basically just remove this board and put it in a case, take the fuse out of it, and run this thing separately. And try to get a good shot with that with the high-speed camera. So maybe just pull the fuse just in case. I don't want to have that glass shrapnel flying around, because my plan is to just run this thing basically open-faced. So let me go ahead and set that up. Alright, we're going to try it without our half-cycle line simulator enabled. Let's just make sure everything's working. Alright, this will be with the half-cycle line simulator active. You know, it looks like it might have arced behind the unit. Let me go ahead and short this thing out. Let's have a look at it. You can see there's very little damage there. Not even much damage here. Oh, I think this all came from the copper up in this area here. I really thought it was going to break down and give us a nice light show right along here. Unfortunately, these traces here just couldn't handle it. Alright, so I'm out inside the motorcycle trailer right now. In this jar here I have some methanol, and this has some top end oiler added to it. Because an automotive meter I would typically use out where I have chemicals like gasoline, brake clean, possibly methanol. I'd like to know how some of these different chemicals react with the plastics that are used to make some of these meters. Specifically, I'd be interested in knowing how the lens is affected. So all I'm going to do is take a Q-tip here, dip it in. We'll just put a moderate amount on the lenses of these 3 meters. And then we'll try it along the lettering as well. And we'll just let that sit for a sec. Alright, let's have a look. Okay, the lens off of this little cheap Harbor Freight meter looks fine. Again, it doesn't look like we stripped any of the lettering off. Looking at the little AN8008, again the LCD's lens looks real good, and no problems with the lettering. Let's have a look at the key sight meter. Again, it looks real good. So normally in the motorcycles I'll use some VP fuel. This is called C16. It's a leaded type of gasoline. Look what that's doing with this ANIG meter. And again, let's go ahead and wipe it off. Oh, that's really bad. Alright, let's have a look again. You can see the lens on the CENTECH meter was not affected. Same thing with the lettering. No problems at all. Look at the ANIG. It actually melted the lens on this. That's not coming off. It did not damage any of the lettering on the meter. You can just see, I mean, that is etched straight into the plastic. And looking at the key sight meter, looks real good. And yeah, same thing with the lens, looks really good. So after exposing these 3 meters to the different chemicals, now that I have them back inside, I'll give you a little bit better view. You can see there were no effects on the CENTECH meter. And the same thing for this key sight meter. Looks really good. And again, here's our ANIG meter. Again, it didn't affect the black plastic or the lettering, but boy, you can see how it just ate that lens right up. This is really rough right now. It just dissolved it. So I guess just a quick summary, if we compare these 2 meters, obviously we can't compare the life of the rotary switch between the two. I never life cycled this EOSUN. I also can't compare our transient testing because I didn't really do any testing on this prior to me modifying the front end of the meter. I am pretty certain though that this meter would have failed at a fairly low voltage just like this one did. Again, with this being a 2000 count meter, of course it's not going to be near as good as this one. That, you know, to be honest, really doesn't bother me so much, except when you're looking at the RPM and, you know, it can only display the 3 digits. And that's a big advantage for this EM135. They actually have quite a few digits that they can use for displaying RPM. Unfortunately, none of the other functions will support all those extra digits. Of course, this is a single display meter, and you can only use one function at a time, where this is a dual display meter, and you can actually display 2 different parameters at the same time. To me, the big problem with this meter, and the reason I would never recommend it, when we had this in the AC volt mode, and I was applying a DC voltage, what you saw this display was actually 2 times the DC voltage. And in my opinion, that's really bad. But the fact that this is an automotive meter, and the fact that I have to actually do the math with this to come up with the meaningful results, that to me is inexcusable. If I have to go through all this math manually, I may as well just use a standard meter like my Bryman. Obviously, this Bryman BM869 is very stable as a tachometer. You just have to manually calculate everything. So for me, that's the whole point of buying a meter like this. And of course, the EM135 doesn't have a problem with that. Again, this EM135 is 3 to 4 times the cost of this little CENTECH meter, but in my opinion, it would be worth it to have the functions work. Unfortunately, I don't really like either of these meters. You know, again, this EM135, even after I modified it, in my opinion, this is still not good enough for what I would want for automotive. Looks like we've picked up quite a few new followers. Glad to have you on board. Hope you're enjoying the videos. I think I'm going to leave you with one last test. See, I have our half-cycle line simulator out, and currently I have the 2 inputs attached to the milliamp jacks. And what I'm hoping here is it's going to arc. There's an area that's a pretty tight clearance down in there, so I don't think we're going to need the fuse. I'm just going to run this thing with the lid open.